So at the end of part one of this lecture, we defined a random variable w, and w is equal to the maximum of a pair of random variables x1 and x2. So choosing a maximum is just one example of a function of two random variables. So we'll work with two random variables, although eventually all of these ideas generalize to as many random variables as we like. In the case of two random variables, the situation typically is we have w as some function g of x and y. And we'll use x and y, although we could just as well have used x1 and x2 for the names of the random variables. And this function g is just some deterministic function. It could be the maximum, or for instance, it might be the sum of x and y, which is something that comes up in many problems, many engineering situations. It could be that g of x and y is the product of x and y. There are a lot of possibilities, and we'll develop machinery to analyze these cases. So in the previous example, we had g was the maximum of two random variables, and we found out that when x1 and x2 are independent, we had some tricky way of finding out the CDF FW of W. In general, finding the CDF can be quite difficult. In some sense, in the last problem, finding the CDF, we just got lucky. The fact is that the random variables were independent and identically distributed, and the max function has special properties that makes it easy to find the CDF. In other problems, finding the CDF or the PDF is hard. And in that case, you're better off thinking first about, when you want to describe this random variable, finding the expected value. And so the expected value of a function of a pair of random variables is really the subject of this lecture. So this theorem generalizes our earlier law of the unconscious statistician in that we say that we have some random variable w, which is a function of both x and y. And in fact, this is a random variable because we do an experiment and the experiment generates a sample outcome. And from that sample outcome, we know what random variable x is and what random variable y is. And then we calculate g of that to generate the random variable w. So an experiment has an outcome that yields a w. And so in the discrete case, we have a PMF PW of W, and we have an expected value, which is the sum over all W, W times PW of W. And in the continuous case, we have a density function, FW of W, and an expected value, which is the integral over all possible values of the PDF times its density. So conceptually, these quantities are simple, but we have an even more difficult situation than we had in previous chapters, and that's that finding this PMF tends to be difficult, and finding this PDF is often quite challenging. So these definitions are good, but they're not so easily implementable because finding these distributions can be complicated. So that's the beauty of this theorem. The beauty of this theorem is that in the discrete case, you take the function and you average it over the joint PMF of x and y, and that gives you the expected value. And in the continuous case, you have exactly the analogous thing. you take the function g of xy for every xy, and you average it over the possible values of x and y. And this averaging then occurs in a continuous way, where the PDF times dx dy is the probability random variables x and y are around little x and little y. The two things are really the same, and you can show that in fact this the the fundamental way of first calculating a PMF or a PDF and then either summing or integrating is in fact completely equivalent to doing this averaging directly with the g of xy function. So our new theorem is really powerful, and in fact it lets us develop formulas for calculating expected values that build on the original formula to calculate more complicated things. So our original formula, if you recall, is that the expected value of g of x and y is equal to the integral of g and x and y times the joint PDF of x and y dx dy. And keep in mind that if I don't write these integrals limits down here, it's because they're over all x and all y. The limits are minus infinity to infinity if I don't bother to write them in. What this theorem says is that we can let g of x and y equal a sum of a bunch of other functions. A1, g1 of x and y plus a2, g2 of x and y, all the way up to some nth function. And of course, these functions can be whatever we wish. And then the expected value g of x and y is the expected value of a1, g1, x and y plus up to all the way up to an, gn of x and y. And now I put this expression into our integral. In your close bracket here. And the point here is that now we just have a simple calculus problem where in fact we have a sum of n integrals, and we can just write this as by breaking them apart into n separate integrals. It's a lot of writing, but it's pretty tedious stuff, right? And now this expression, of course, here, this is the expected value of g1 of x and y. And this expression here is the expected value of gn of x and y. And the thing to remember here is you don't really want to do this derivation ever again. What you really want to do is be comfortable using this property of the expected value. The expected value of the sum of things is the sum of the expected values. And if there are some weighting factors, like a1 through an, these weighting factors just become constants out front. They become the same weighting factors on each term. Often in textbooks, you'll hear people say, oh, this is the linearity of the expectation operator. Essentially, you can you can multiply expected values by constants, and then the expected values are multiplied by those constants. And you can take sums of things and their expected values, and the expected value of a sum is the sum of the expected values. So all the typesetting on this slide just makes the point that exactly the same steps of the proof we just did are true whether you work in discrete random variables by summing PMFs, or you work with integral expressions and continuous random variables. In either case, the expected value of the sum is the sum of the expected values. So that was a very general theorem, and the special cases of the theorem are important in their own right. So in this example, we have that A1, G1 of x and y is just equal to x, and A2, G2 of x and y, my y is quite terrible, is just equal to y. And the theorem says that the expected value of x plus y is the expected value of x plus the expected value of y. And this is true for all random variables x and y, that the expected value of the sum is the sum of the expected values. It would be nice if the same kind of thing was true for the variance, but in fact it isn't. For the variance, we have something more complicated. The theorem says that the variance of the sum is equal to the variance of x plus the variance of y plus 2 times this cross term, which has something to do with x being different from its mean and y being different from its mean. How this expression falls out of the definition is kind of instructive, so let's talk about that. So we know that e of x plus y is equal to ex plus ey, and for convenience, we'll call those mu x and mu y. And then the next step is to recall that the variance of x plus y has to be equal to the expected value of the random variable, which is x plus y, minus its expected value, which is mu x plus mu y, and then the whole thing has to be squared. And now we'll rearrange this one more time. This is x minus mu x plus y minus mu y, and then the whole thing is squared. And then you have to square these things, and you get, well, you get x minus mu x squared, plus you get y minus mu y squared, plus you get 2 times the product of the cross terms. And then we have to think about this just a little bit more and realize, like, oh, this is like a g1 of x, and this is a g2 of y, and this is a g3 of x and y. And putting these pieces together, you get the expected value of the first term plus the expected value of the second term plus 2 times the expected value of the third term. And of course, these pieces match up perfectly. This is variance of x, and this is variance of y, And this is this cross term. That's exactly what appears up at the top of the page. So this cross term is important because it tells you that the variance of x plus y, it could be the variance of x plus the variance of y. It could be bigger than that, or it could be smaller than variance of x plus variance of y. In some sense, it's possible that the x plus y in some way is less random than the randomness contributed by each individual piece. So this cross term is sufficiently important. It has its own fancy name, and that fancy name is covariance. And we write COV of x and y, and it's the covariance of random variables x and y. And it's exactly this expected value of x minus its mean mu x times y minus its mean mu y. So the thing to remember here is that the variance of the sum x plus y is equal to the variance of x plus the variance of y plus 2 times this covariance of x and y. And so the way to think about this is that the variance of a random variable kind of is measuring its randomness around its expected value. So the variance of x plus y is giving you kind of the randomness of the sum x plus y. And that variance is, or that randomness is equal to the randomness in x plus the randomness in y. And then we have this covariance term, and the covariance term actually can be either positive or negative. So there's one possibility is that the variance of x plus y is actually greater than the variance of x plus the variance of y. And this occurs when the covariance of x and y is greater than 0. And the other possibility is that when you add up x and y, you get something that's less random than the individual pieces. In this case, the variance of x plus y is less than the variance of x plus the variance of y. And this corresponds to the covariance of x and y being less than 0, simply because when it's negative, it's a negative contribution up here in this term. So it's important to understand kind of what is happening with covariance. When covariance is positive, what we see is that when x is greater than its mean, it tends to be that y is greater than this mean, because the covariance is positive if generally this product term is positive. On the other hand, you can have negative covariance, and where you get negative covariance, it means that the product of the x term and the y term tends to be more often than not a negative number. And what that corresponds to is if x is bigger than its mean and it's positive, the x term, then the y term will have to be negative, and so y is less than its mean. And sort of in simple terms, the covariance is negative if when x goes up, y tends to go down, or vice versa. When y goes up, x tends to go down. So the units of covariance can be kind of complicated because the units of x are something, say meters, and the units of y are something, say kilogram. And then covariance will have the units of kilogram meters. And that may or may not be something that has physical meaning for you. So this can get tricky because somebody will tell you, well, the covariance is 6,000,003, and you're not sure if 6,000,003 is a big number or a small number in the units you're working in. Fortunately, covariance has a normalization property that's a little bit magical and kind of awesome. And we express normalized covariance as a term in its own right that we call rho. And this is called the correlation coefficient of random variables x and y. And, and this correlation coefficient is really quite simple. You take the covariance and you divide by the square root of the variance of x times the variance of y. And of course, the square root of a product is the product of the square roots. And the result is this rho is the covariance of x and y divided by the standard deviation of x and divided by the standard deviation of y. Because the units of covariance are the units of x, say meters, times the units of y, say kilograms, what we do when we divide by the standard deviation of x and the standard deviation of y is that we get rid of the units because sigma x is in the units of x and sigma y is in the units of y. The result is that the correlation coefficient is unitless. And this unitless property gives it kind of good upper and lower bounds. And the theorem says that rho of xy has to be less than or equal to 1 and greater than or equal to minus 1. And so in normalized terms, rho xy equals 1 is the maximum positive correlation. And rho xy equal to minus 1 is sort of the maximum negative correlation. It's as opposed as two random variables can be. And this reminds me of something I forgot to mention. What about if the correlation coefficient is right in the middle? For instance, if rho xy equals 0. Well, since the standard deviation sigma x and standard deviation sigma y both have to be positive, rho xy equal to 0 in fact corresponds to covariance xy being 0. And so how do we get 0 covariance? And so this is actually pretty straightforward. 0 covariance is implied by random variables x and y being independent. So x and y independent implies that, for instance, that the joint PDF of x and y is product of the marginals. And this implies that the expected value of x minus mu x times y minus mu y, well, we write this as this double integral. And now when you write the joint PDF, you write it as the product. And then this actually factors as x minus mu x fx of x dx into separate integrals. And this is equal to x minus mu x is expected value of y minus mu y. And this is equal to 0 times 0, and that's 0. So if in fact what we see here is that rho equal to 0 is a consequence of independence. So in some sense, what we're going to show is that rho xy kind of measures dependence. Like when rho is very close to 1 or to minus 1, x and y are strongly dependent. In fact, as rho gets close to 1 or -1, we say the random variables x and y are highly correlated. On the other hand, when rho is close to 0, that kind of gives us a kind of a clue that the dependence between x and y is weak, and in fact, it might mean that x and y are independent. Okay, so here we'll wrap up and stop, and we'll just keep in mind that this correlation coefficient rho is between -1 and 1, and we'll start doing some examples to get a sense of what it means for it to approach 1 or to approach -1, and that'll be in the next part of this lecture. So this homework problem addresses kind of the extreme cases of how we arrive at rho equals 1 or rho equals -1. So this problem is 557, and in fact, it's in the wrong section of the book. It really should be in section 5.7. In section 5.5, rho hasn't even been defined yet. So in this problem, x is an arbitrary random variable, so it has some kind of an expected value mu x and some kind of standard deviation sigma x. And now in that case, we can find the expected value of y. It's the expected value ax plus b. And using the linearity of the expectation operator, it's a ex plus b, which is a mu x plus b. And of course, we'll call this uy. Similarly, the variance of y, is the variance of ax plus b. And if you remember our earlier theorem, the offset b doesn't change the variance. The variance changes by a squared. So it's a squared times variance of x. So we can write this as sigma y squared is equal to a squared times sigma x squared. And it's tempting to take a square root, but you have to be careful here because the a could be positive or it could be negative. Now we're ready to write down the covariance of x and y. Covariance of x and y is the expected value of x minus mu x times y minus mu y. But random variable y is defined in terms of random variable x. Y minus mu y is a x plus b minus a mu x plus b, and this simplifies to x minus mu x. And here we get a times x minus mu x because we get a plus b and a minus b that cancel out. And the result is that we have a times the expected value of x minus mu x squared. That's equal to a times the variance of x. Now we're ready to evaluate the correlation coefficient. Rho of xy is equal to the covariance of x and y divided by the square root of sigma x squared times sigma y squared. So the covariance is equal to a times the variance of x. In the denominator, we have variance of x, and then we have variance of y, which is equal to a squared times sigma x squared. And now putting this together, we get that that we have sigma x squared canceled by the square root of sigma x squared times sigma x squared. And we're left with a over the square root of a squared. And this is where we have to be careful because the sign of a matters. In all cases, whether a is less than 0 or greater than 0, the square root of a squared is greater than 0 because a squared is positive and we always take the positive square root. However, when a is greater than 0, and we get rho of xy is simply equal to a over the square root of a squared, and both are positive, and this is 1. But if a is less than 0, then we get rho of xy is equal to a over the square root of a squared, but the numerator is negative and the denominator is positive, and the two things have the same magnitude, so the result is minus 1. So this algebra is kind of messy, but the point that we're making here is important, and that's if the correlation coefficient is equal to has magnitude equal to 1, then the two random variables x and y aren't really two different random variables. It means that one of the random variables, in this case y, is really just x expressed in some other units. For instance, it could be that x is a temperature in Celsius and y is the same temperature in Fahrenheit. It's really the same temperature. We're just choosing two different units to represent it. And this is the most common place where you get rho equal to +1 or -1, it's that the one random variable is the same as the other, just in a different kind of a unit. So here is the typeset solution from the solution manual. And of course, it's the same, and maybe you'll find it more clear than my handwriting. And we'll stop here and we'll think more about, we'll look at examples of rows close to 1 but not exactly 1 in the next segment.